So hello friends, welcome to the MPLS class. Myself Debasish Chakrabory. I'll be giving you this training curriculum on MPLS. So today we'll be covering the introductory concepts of MPLS. MPLS is a magnificent technology, and I can give you one fact that although this particular technology belongs to an area belongs to an era when these virtual network or cloud, they are not into existence, right? But still MPLS is that technology which is giving a neck to neck competition with the new technologies that have come up today, right? And if you are going for any kind of enterprise network or service provider network, then MPLS is still a very indispensable technology. So let us start with the introductory concepts of MPLS. Okay. So before going through these definitions, I'll first present you with a diagram. So this is my diagram. This is a very simple topology where you can see that these are R1, R2, R3, R4, R5. These are all routers. They are having networks like this. Their interconnecting networks are like this. This is 12.0.0.0/8. That is 23.0.0.0/8. That is 34.0.0.0/8. And that is 45.0.0.0/8. In fact, whenever I configure or whenever I design any topology, I used to configure the network numbers in this way so that it becomes easy to understand and easy to remember. Because if you consider this network, this is connecting between router 3 and router 4. So for that reason, I have numbered it as 34.0.0.0 network. And as this F0/1 interface belongs to router 3, so this is 34.0.0.3. And as this F0/0 interface belongs to router 4, so that is 34.0.0.4. Right. Don't consider them as 34.0.0.1 or 34.0.0.2 because it is the most common type of topology that you will find that if two routers are connected by a 34 network, so one side should be 34.0.0.1, the other side should be 34.0.0.2. But here I am not following that particular design also. I have numbered this as 34.0.0.3 and this as 34.0.0.4 just to remember it more that this 34 network, it actually connects router 3 and router 4, and on this side it is router 3 and on that side it is router 4, right? Okay. So in this way, this F0/0 is 12.0.0.1, this F0/0 is 12.0.0.2, this F0/1 is 23.0.0.2, this F0/0 is 23.0.0.3, this F0/1 is 45.0.0.4, and this F0/0 is 45.0.0.5. I hope it is 100% clear. And in this router 5, I have configured a loopback interface or a loopback network that is 5.5.5.5/32. Okay. Now, what is the purpose of this diagram? This particular diagram will be leading us to the first definition of MPLS, and that is MPLS domain. Suppose I have applied MPLS between these routers. That is, MPLS is working here, 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 and here. So in that case, from R1 F0 by 0 to R5 F0 by 0, this entire area is my MPLS domain, right? Anything which falls outside, either on this side or on that side, will be a non-MPLS domain or a simple IP domain, right? So this is the first definition. So what is an MPLS domain? It is very simple to remember. It is actually the area where MPLS is working. So in this particular area MPLS is working, so it is the MPLS domain, right? Now I move into the other definition parts. Now in case of an MPLS domain, we should be knowing these definitions: LSR or level switching router, which is also called level switched router, then edge LSR, then LSP or level switched path. Now what are the definitions? LSR or the level switching router, it only swaps levels and forwards labeled packets. Edge LSR, it connects MPLS domain with a non-MPLS domain. They push levels, they pop labels, and can do layer 3 lookups. LSP or level switched path, this is an end-to-end virtual path consisting of the routers and established prior to sending any MPLS data, right? Now I move into the proper explanations. Once again into this topology. So what are the LSR? All these routers are LSR router, right? So they are all level switching router. Now you should be keeping in mind that level switching routers are not some specific routers or special brand or special model of routers. If you are going to any Cisco store and if you are asking them to give you a router which is a LSR, they'll be simply confused because the router is simple as a router. Whether it can work as an LSR or not, that depends on whether the operating system, the iOS, which is inside the router, actually supports MPLS facility. So if you are equipping your router with MPLS features, then definitely your router can be a LSR. So all these routers, as they are implementing MPLS, so they are all level switching routers or LSR. The routers which are lying inside the path or inside the MPLS domain, rather who are completely members of MPLS domain, because if you are considering router 2, router 3 and router 4, you can very easily see that both of their interfaces belong to the MPLS domain. So the routers whose all interfaces belong to the MPLS domain are the normal LSR or core LSR. So these are actually the core LSR. And if you are considering this router and this router, that is router 1 and router 5, in their case, they are actually a connecting link between the MPLS domain and into some other domain. Maybe it is an IP domain, right? So that's why they are called edge LSR. Now, when we are considering the edge LSR, we have to remember two other terms. One is ingress LSR or ingress edge LSR. Another one is egress edge LSR. Ingress and egress. So what is ingress? If you find that a data is traveling from router 1 to router 5, so in that case, router 1 is actually putting that data into the MPLS domain. So the edge LSR who actually forwards a data into the MPLS domain is called the ingress edge LSR. And if you consider R5, here the data actually leaves the MPLS domain. So for that reason, this router is considered as the egress edge LSR. Right. Now, one thing you have to keep in mind, these two terms, egress and ingress, they are actually relative terms. Why relative term? Because ingress or egress depends with respect to the direction of data. If your data is flowing from R1 to R5, then definitely this is ingress and this is egress. Whereas if the data is flowing from R5 to R1, this is egress, this is ingress and this is egress. So whether you are calling it ingress or egress, that actually depends on the direction of data, right? Okay. So now I have mentioned here in the previous slide that a normal LSR only swaps labels and forwards the labeled packets. That means if you are considering these three routers, they can swap label and they can forward the labeled data, right? What is a label? Coming to that just a few moments later on, right? Definitely you need a 100% clear concept on label. So I'll be moving into a greater detail for label, but for the time being, just consider this term label. So there is something which is called label, and what this router 2, router 3 and router 4 can do, they can swap label. That means if a data is coming towards them with a certain level, they can change that level with some other level, right? So if a data is coming to R2 with a particular level, the R2 router can exchange that level with some other level. This is number one job, that is called swapping of level. And number two is, after swapping the level, they can forward the labeled packets or the labeled data, right? So they can receive and send labeled data, and at the same time they can swap the labels. Now what about these edge LSRs? The edge LSR, as I have already discussed, it connects the MPLS domain with a non-MPLS domain, and it will push level, pop level, and can do layer 3 lookup. So that means whenever a data is entering into the MPLS domain, this R1 will push or rather attach a label to that data. So for the first time, that data gets a label from the hands of R1. This is called pushing the label or attaching the label. And when the data is leaving the MPLS domain by getting the hands of router 5, their router 5 actually takes out the label, which is actually called popping up or extracting the label from the data, right? So the normal data gets a label when it enters the MPLS domain, from whose hand? The edge LSR, or rather the ingress edge LSR. And when the data leaves the MPLS domain, in that case the label is popped. Again, who is doing it? The egress edge LSR, right? So these are the functions of the edge LSRs and the normal core LSRs, right? And now the third definition, that is level switched path. This is an end-to-end virtual path consisting of routers and established prior to sending any MPLS data. Now you should be paying attention to this particular word, virtual path, and this particular phrase, prior to sending any MPLS data, because these two things deserve some special mention. Why? So that means LSP is something or level switched path is something that is established from R1 to R5, but it is not a physical path. This is a physical path, obviously. This is a physical path. There must be some kind of connectivity, physical connectivity between R2 and R3, R3 and R4. But if you consider a path which is running from R1 to R5 that is created by MPLS, that particular path is a virtual path. It has got no physical existence. This is number 1 point. And number 2 point, which is very, very vital, that is, that particular path is established before sending any single data. That means that path becomes ready before the first data comes. So try to keep these two things in your mind. One is virtual path and another one is it is established or signaled even before sending any single bit of data. Okay, fine. Now I move into the other definitions or other certain informations like any LSR. Just a second. I need to explain this thing also. I should have explained this later on, but I want to explain it right now. This particular phrase can do layer 3 lookup for the edge LSR. So what is this? Can do layer 3 lookup. Once again, if I go to this diagram, see, if you consider this router 5, it is the endpoint of the MPLS domain. Now, if the data which is coming from R1 and have reached router 5, that data has to be forwarded into a domain which is not an MPLS domain. Now, definitely as a router is connected to that domain, obviously it is a network layer domain because routers always work in network layer or layer 3. For that reason, now if the data has to be forwarded to some other distant location, this router also has to do a network layer lookup. That is, it has to consult its routing table to find out where is the destination, where should be the next hop, and so on, right? So that means this router is also responsible for doing some kind of layer 3 lookup or network layer lookup. And in most cases, it is obviously an IP lookup, right? Now back to this slide once again. Any LSR can send MPLS packet or IP packet to its neighbor. So to specify that it is sending MPLS packet, it uses hexadecimal values of 8847 or 8848 in the ether type field of the data link layer header. Although it sounds very difficult, but it is a very, very simple concept. See, what I am telling is this R1 router can also send a data which is not labeled, right? It is not a mandate that it should be always labeling a particular data whenever it is forwarding it into the MPLS domain, right? You should not have this misconception that every data that passes through the MPLS domain must be having a label on it, right? It can be a normal data also or IP data also. Now, this router must inform router 2 that whether it is sending an MPLS data or whether it is sending a normal IP data. In the same way, this kind of information should be also present when R2 sends something to R3, when R3 sends something to R4, and so on. Now, where is this information present? It is actually present in the data link layer header. I think all of you know about the OSI model, and you know that whenever the data passes through the different layers of the OSI model, they get certain encapsulations which are called their headers, right? So in the data link layer header or the layer 2 header, there is a particular field if you see the data link layer header, if you can see a picture of the data link layer header, it's very easy to find in any networking book. You can easily find a picture of the data link layer header. You will find that there is a field which is called ether type. Now in the ether type field, it puts a hexadecimal value of 8847 or 8848. Now whenever a data is coming from R1 with 8847 or 8848 hexadecimal value in its ether type field of the data link layer header, whenever R2 sees that, R2 understands that this is a MPLS data. So I have to give it a treatment for MPLS. And if the data is coming without those values in its layer 2 header, then R2 understands that no, this is a normal IP data and it should be receiving normal treatment for any IP data. Understand? So this is a very simple concept, although it sounded very difficult, but I hope it is now very, very simple to all of you. Now coming to MPLS applications. See, MPLS is a very, very versatile technology. For that reason, MPLS is still prevalent and in full swing even today when we are going for virtualized networks, we are going for SDN, software defined network, we are going for the cloud. Still, we cannot avoid MPLS. So this is actually the reason why MPLS cannot be avoided, because it can encompass or it can serve all the services of networking. If you consider networking can give you these services. Either it is giving you unicast routing or multicast routing or VPN routing or traffic engineering or quality of service. If you consider any network, you cannot think anything beyond this, right? VPN is giving you security, quality of service is giving you some guaranteed service, traffic engineering is giving you the facility to use the other paths or the alternative paths. More on this later on, because there will be an entire topic dedicated for traffic engineering when I'll be in the last phase of this MPLS tutorial. So if you consider network, if you understand network, you will see that network is nothing but a collection of all these services. And all these services are very, very suitably served by MPLS. Now, regarding these services, we have to remember certain things, that is FEC or forwarding equivalence class, then protocol to build the FEC and protocol to manage the levels. Now, I'll be going into the definition for FEC a little bit later on. But before that, I'll give you these informations that if you consider IP unicast routing, the FEC is based on routing table. For multicast routing, the FEC is based on multicast routing table. For VPN routing, it is based on VPN routing table. For traffic engineering, it is based on something which is called tunnel. And for quality of service, again, it is based on routing table. Which protocol is used to build the FEC? In case of unicast routing, it is any unicast routing protocol. In case of multicast routing, it is protocol independent multicast or PIM. Those who know some complex features of networking, I think you have come across this term multicast routing, and there are several routing protocols which can do multicast routing, like say DVMRP or distance vector multicast routing protocol. You can have MOSPF or multicast OSPF. You can also have PIM, which is protocol independent multicast. Now, in case of MPLS, the only multicast routing protocol that is used is PIM. It is not using DVMRP or MOSPF. It is only considering PIM. For VPN routing, the FEC is actually built by a combination of IGP or any interior gateway protocol and border gateway protocol or BGP between the customer and ISP, and MPVGP for ISP core. I'll be moving into these details later on. And for traffic engineering, the FEC is entirely dependent on any kind of link state protocol. It can be OSPF or ISIS. For quality of service, it can depend on any routing protocol. Finally, what are the protocols that manage the different levels of MPLS? In case of unicast routing, it is TDP or LDP, coming to this very soon. Tag distribution protocol or level distribution protocol, coming to this very soon. Then for multicast routing, it is PIM version 2 extended or protocol independent multicast. For VPN routing, it is multi-protocol BGP or the modern version of BGP. For traffic engineering, it is done by a protocol who has got a peculiar name and a more peculiar short form. Its name is Resource Reservation Protocol and its short form is RSVP, right? It is not Resource Reservation Protocol. Reservation Protocol should be RRP or something like that, but they have shortened it as RSVP, right? And for quality of service, again TDP or LDP. Understood? Now first I would like to explain this term FEC. So FEC, if you are going for its definition, here FEC or forwarding equivalence class, this is the definition: forwarding information for any particular destination, and this is called categorizing that particular destination for a particular FEC. Each data for that destination will receive the forwarding decision as per that FEC, right? So this is actually the definition. That is, FEC is actually a treatment for a group of data that is destined for a particular destination. A group of data which is moving towards a particular destination should be receiving a uniform and similar forwarding treatment. Once again I repeat, whenever a group of data is moving towards a particular destination, they should be receiving a uniform and similar forwarding treatment, right? And that particular treatment is called forwarding equivalence class, right? So forwarding equivalence class is nothing but a treatment for any group of data which are destined for a particular destination. I hope it is now clear. Now I'll be moving into the level, which is actually the main thing, or rather the atoms and molecules of MPLS. So at first I'll read out this thing. So modern form of routing where packets are forwarded on the basis of level switching. Level switching. Keep these two terms in your mind because I'll be discussing something regarding this. In fact, you have to understand why it is called switching, right? Although it is performed by routers, still why we are not using the term routing, why we are not calling it multi-protocol level routing, why we are considering it as switching. Now what is a level? Level consists of a group of information to forward packets for any particular destination, right? And each level is 32 bits. There can be more than one level for any particular packet, MPLS level equals to level header 20 bits plus TTL 8 bits plus EXP bits, that is 3 bits in size, and plus bottom of stack bit, that is 1 bit in size, that is altogether it is 32 bits. The bottom of stack bit indicates whether this level is the last level of the stack or not. Now what is this level? So a level is something that is attached to a data, right? It is just like any header. As there is a IP header, as there is Ethernet header, as there is TCP header or UDP header, in the same way, MPLS level is actually a header that is attached to the data, which will receive a MPLS treatment. That particular header has the size of 32 bits. And inside these 32 bits, the first portion or the level header is 20 bits. Then the second portion or the TTL, time to live. TTL or time to live, I think all of you have this idea what is a TTL. This is actually the number of jumps that a packet can do, and it is expressed in 8 bits. So if you are providing a TTL value of 2 bits, that means it can jump up to that number of routers that is permissible by 2 bits. So time to live 8 bits, EXP bits. Now this EXP bits, which is 3 bits in size, this particular area contains the quality of service information. I have already discussed that MPLS is used for quality of service also. So this EXP bits, it is actually containing the information related to the quality of service for that particular data. And finally, the bottom of stack bit or 1 bit. Now this bit definitely can be either 1 or 0. So if the bottom of stack bit is equals to 1, that means this is the last level. But if it is not 1, if it is 0, that means it is not the bottom of stack. That means there must be some other levels below that particular level. And it is actually the level stack, right? So if you consider the levels are something like this. If this is the data, this can be a level, this can be a level, and this can be a level, right? Now for this level, the bottom of stack bit, this particular one, will be 0. For this level it will be 0. For this particular level it will be 1, because this is the actual data. So it indicates that this is actually the last level, right? So if you want to see the level, if a picture of the level, I will show that. So this is actually the position of the level or position of the MPLS header. So you see the MPLS level is actually inserted between the data link layer and the IP header. So that means that 32-bit information that I have discussed right now, it is actually inserted in between the data link layer and the IP header, right? Now, for this reason, MPLS is sometimes considered as layer 2.5. Why layer 2.5? Because if you are considering OSI model, IP is layer 3. So IP header is a layer 3 header. This data link layer is layer 2. Now as MPLS is coming in between layer 3 and layer 2, the entire MPLS technology is sometimes considered as layer 2.5, right? I hope it is clear. Okay. Now first I will discuss this thing, that is TDP and LDP. We have already come across these two terms in this slide, where TDP or LDP, they are actually responsible for managing the labels, right? Because there must be some protocol who will be generating the labels, who will be responsible for mapping between the labels, who will be responsible for attaching the labels to the data. So these things are done by TDP or LDP if you are considering normal unicast routing or quality of service. So let us discuss TDP or LDP. Okay. So label assigning for a particular FEC, exchanging the labels, creating the label information base, coming to this very soon. What is this label information base? And finally deciding the label forwarding information base, once again coming to this very soon, is done by two protocols, TDP or LDP. So TDP, full form Tag Distribution Protocol, is Cisco proprietary and uses TCP port 711, whereas LDP or Level Distribution Protocol is open standard and uses TCP port number 647. I don't think these things deserve some special mention because all of you know that the different forwarding protocols, they are somewhat dependent on TCP and IP. And in many cases, these forwarding protocols, they use certain port numbers of TCP and IP. For example, if you are considering BGP or Border Gateway Protocol, that is a routing protocol that is entirely dependent on TCP. Right. Again, if you consider EIGRP or OSPF, they are depending on IP, certain ports of IP. If you are considering RIP, it is using certain ports of UDP. So these forwarding protocols, whether they are MPLS labeling protocols or routing protocols, they are in some way or other dependent on certain ports of either TCP or IP. So here we see that TDP depends on TCP port 711 and UDP depends on TCP 647. TDP or LDP discovers neighbors by multicast hello packets and maintain neighborhood by keep alives. Neighbor router ID is the neighbor ID. So first of all, have a look in this particular area, Cisco proprietary. This TDP is Cisco proprietary. That means you can use this particular protocol only for Cisco router. Whereas for any router, with be it Cisco or be it Juniper or any other vendor, you can use LDP. So it entirely depends upon you which labeling protocol you should be using. But one thing, keep in mind that there is no advantage of using TDP over LDP or vice versa. You can use any one, whichever you feel like, right? It is entirely depending on your vendor. If you are using an all Cisco platform, you can very easily use Cisco proprietary TDP. If you are using a multi-vendor platform, go for LDP. Even it is not at all unusual to come across a router where TDP is using at one end, is being used at one end, and LDP is being used at another end. Say suppose if you consider this R2, maybe TDP is working here and LDP is working here. But one thing you must be careful. If you are using TDP here, TDP should be here also, right? If you are using LDP here, LDP should be here also. You can use them at different interfaces, but at the connecting interfaces, you should be careful of using the same labeling protocol. Now, if you are using TDP here, and if this particular router is not a Cisco router, no issues. You simply remove TDP and apply LDP here. LDP can be applied here also, as it is a non-Cisco router. I hope this is clear. Now, coming to this particular area, TDP or LDP discovers neighbors by multicast hello packets and maintain the neighborhood by keep alives. So what is this? Once again, if you consider this picture, suppose TDP is working between these two routers, R2 and R3. So these two routers should be considering them as TDP neighbors. I think this concept is clear to you because all of you know about routing. If you are considering the modern routing protocols like OSPF, EIGRP, ISIS, then BGP, they all establish neighborhood, right? So here also TDP or LDP, they establish neighborhood between the routers, and that neighborhood is established by using hello packets, and the neighborhood is maintained. That is, whether my neighbor is still there or gone, that is actually understood by exchanging the keep alive messages, right? Fine. And neighbor router ID, RID is router ID, is the neighbor ID. So that means, suppose this particular R3 has a router ID of 3.3.3.3. So R2 will be identifying R3 as its TDP or LDP neighbor by using that address. Once again, I repeat, suppose this particular interface is 23003 and R3 has the router ID 3.3.3.3. Now in that case, R2 will be considering the TDP neighbor as 3.3.3.3 and not 23.003, right? And here, although I am not going into the practical part today, but for doing the practicals in future, I just give you one information, that is, always provide these routers with certain router ID, manual router ID, because I have seen with my own experience that if you are not providing them with any manual router ID, then definitely this 23003 will become the router ID for R3, right? And in that case, R2 will try to establish the neighborhood by using this address, that is the physical interface address. And in that situation, sometimes the neighborhood is denied, right? So if the physical interface is being used for neighborhood, it is sometimes denied by TDP or LDP. I don't know why, but I have come across this in several situations. So this is my advice to you. Always configure manual router ID for these MPLS participating routers. It is not at all any big deal. Just configure any loopback and it will be considered as a manual router ID. So whenever this router will establish a neighborhood, it will accept that manual router ID or loopback router ID. Right. Okay. Now moving into the other definitions. So once again, I visit this line. A label consists of a group of information to forward packets for any particular destination, right? A group of information to forward packets for any particular destination. Now I hope, as all my friends are into networking, you people know that what are these informations that are so necessary for forwarding the packets. Definitely two informations are have the highest priority, that is next hop and the exit interface. That means if you are considering this diagram, if R1 wants to forward something to R5, it must remember that my next hop is 12002 and my exit interface is F0 by 0, isn't it? If R2 wants to forward something to R5, it should remember that my next hop is 23003 and my exit interface is F0 by 1. Now who gives them this information? Who creates this sense in these routers? Definitely the routing protocol. It is actually the duty of the routing protocols to provide this kind of a sensibility into the routers. Otherwise you can do it manually. If you are going for static route, you can specify which is my next hop and what is my exit interface. So any kind of routing must be working to get these two informations. Maybe it is a static routing or maybe it is a dynamic routing using any routing protocol. Understood? So what happens when a MPLS domain works? So there are actually certain steps. Now I'll be discussing those steps. So this is step 1, then step 2, step 3, step 4, step 5, and finally step 6. So let us now discuss these steps. This is a very, very interesting story. Now before starting this story, I would like to mention one information which is very, very vital. That is why MPLS is so important, or what is actually the advantage point of using MPLS. Because if we consider the working principle of MPLS, it is similar. It is somewhat similar to normal IP forwarding, right? Normal IP forwarding. So what gives it the better edge? Why it is preferred more over normal IP forwarding? The answer is, in case of MPLS, the previous hop router is telling something to the next hop regarding the forwarding of the data. Once again I repeat, in case of MPLS, the previous hop router is helping out the next hop router as to how to forward the data. That means whenever, say, R2 is handing over a data to R3, forwarding a data to R3, it is also helping R3 to take the decision of how to forward the data to R4, right? This is the actual story behind the popularity of MPLS. See, when I first started learning MPLS, I was into a confusion. I couldn't come to terms with the fact that why this particular technology should be preferred over normal IP forwarding, right? It looks very simple as normal IP forwarding. Nothing very special. Some kind of lookups, as happens in case of IP forwarding, here also some kind of lookups, they are taking place. So why we should be replacing IP forwarding with MPLS? Then finally, after a long hard study and after going through the lines and words of the different texts, I have realized that this is actually the factor. In case of normal IP forwarding, there is no one to tell the present router from behind as to how to forward the data. In case of normal IP forwarding, R2 will not be telling anything regarding the forwarding decision to R3. But in case of MPLS, R2 will definitely instructing something, will make the work of R3 much simpler by providing certain informations as to how to forward the data. So let us now discuss the steps. So each router decides the forwarding information for any particular destination, and this is called categorizing that particular destination for a particular FEC or forwarding equivalence class. Each data for that destination will receive forwarding decision as per that FEC. That means if you consider R1, R1 understands, R1 knows that if I want to reach 5.5.5.5/32, that means here, my next hop should be 12.0.0.2 and my exit interface should be F0/0. R2 knows that if I want to go to 5.5.5.5, my next hop should be 23.0.0.3 and my exit interface should be F0/1. Similar things also happen for R3, R4, and finally when you go to R5, R5 knows that there is no next hop because it is directly connected to my loopback. The destination network is directly connected to my loopback. Now, who provides this sense? Obviously, any routing, any form of routing. Maybe it is static routing or maybe it is any dynamic routing protocol that has provided this information to this router as regards the next hop and the exit interface. I hope this is 100% clear because all of you know this. Now step 2, the most interesting thing happens here. Each FEC information is compiled in a fixed size information called label. Each router first decides its own label for that particular destination and it is called the local label for that destination with respect to that router. So you see, R1 has already decided that for this particular destination 5.5.5.5, my next hop is 12.0.0.2 and my exit interface is F0 by 0. So these two informations, yes, there are also other informations, but for sake of simplicity, I am just considering these two informations, that is next hop and the exit interface. They are compiled in a form which is called label. So say level 1 is the level that is created by R1, level 2 is that one which is created by R2, level 3 is created by that one by R3 and so on. So these levels, they contain the next hop and exit interface for the respective routers. So level 1 contains informations for R1, level 2 contains information for R2, level 3 information for R3 and so on. These levels which are at first created are called the local levels. So level 1 is the local level with respect to R1, level 2 local level with respect to R2 and so on. Fine? Okay. Once again I repeat, these levels may be containing other informations also, but for the sake of simplicity and to understand the mystery of MPLS, I am just considering these two informations inside these levels. And another thing, I have named the levels, right? Level 1, 2, 3, 4 and 5. In reality, you will never find labels having names. In fact, they have numbers. Their numbering starts from 16, right? So when we'll be doing the practicals, we will understand that in a much clear way. For the time being, let us consider the levels having names also. Now step 3. Each router exchanges its level information for that destination with its neighbors. Right. So this particular step happens in different passes. So all the passes are not mentioned here, but it is easy to understand. At the very first pass, router 1 sends its level 1 information to router 2. Router 2 sends its local level information to router 1 and router 3. Router 3 sends its local level information to router 2 and router 4. In this way, all routers, they exchange their level informations with their adjacent routers. Right? And this happens in several passes. Why in several passes? Because if you consider router 3 has a local level 3. It also has two levels, level 2 and level 4 from router 2 and router 4. Now it will definitely exchange this level 2 with router 4 and level 4 with router 2. Right? That means in the second pass, they will be exchanging the levels that they have received in the first pass and so on. So what happens? Finally, in step 4, when all routers have exchanged all labels for that destination, each one has a label information base or LIB. We have come across this term little bit earlier. It consists of the local label and the collection of all outgoing labels for that destination. So you see, for R1, from R1 to R5, each router has all the labels. Obviously, one label is their respective local label, and all the other labels, they are considered as the outgoing labels. So for R1, level 2, 3, 4, 5, these are outgoing labels. For going to loop back 1, this 5.5.5.5. For R2, level 1, level 3, level 4, level 5, these are the outgoing levels for reaching 5.5.5.5. Here I would like to mention one thing. This level information base is obviously with respect to a particular destination. And if you consider several other destinations like these, for each of these destinations, all these routers should have the LIB. That means each destination has a specific level information base. Once again, I repeat, each destination reachable by any router has its specific level information base. Right? So the level information base collection can take up a substantial amount of router memory also. For this reason, MPLS is not possible if you are going for very low-end routers. Right? If you are considering Cisco, Juniper, these big brands also, if you are going for their very lower level routers, which have low memory, low CPU processing speeds, in those cases, MPLS is not possible. Because MPLS level information base and all other structures like these will definitely take up substantial memory space of the routers. So this you have to be careful. In fact, when I started this lecture, I have told you that whether a particular router will be supporting MPLS or not, that depends upon the version of the operating system. And you will be definitely seeing that the version of the operating system which supports MPLS will not be installed in a router which has very low-end hardware, isn't it? If you are using a Cisco 800 series router or a very low-end series router, in that case, you will not find MPLS because MPLS supporting iOS will not get installed in those models. Okay, fine. So what happens in this particular stage, all the routers are now ready with a level information base, and this level information base consists of the local level, one local level, and all outgoing levels as received from all the routers of the MPLS domain. Very interesting thing to note. Suppose if you consider R3, R3 is also considering level 1 and level 2, which are actually on the far side. These are not the near side to 5.5.5.5, right? If we consider this topology, obviously R3 should be considering these two levels, level 4 and level 5, because these two levels are sent by R4 and R5, which are nearer to the destination. Whereas levels sent by R1 and R2, they are far away from the destination. Still R3 will retain these levels, right? Still R3 will retain these levels, and in this respect, this particular nature of MPLS has somewhat similarity with how OSPF LSA database is actually created. Whenever OSPF routers exchange their LSA, they don't care whether it is sent by a neighbor which is nearer to the destination or not. They maintain all the LSA for any particular destination as sent by all routers. Here also, the labels for any particular destination, be it a nearer router or be it a further away router, all the labels will be retained. This is very important point. Now in step 5, each router then maps its local label for that destination with the most appropriate outgoing label for that destination. This is decided on the basis of the most appropriate next hop for that destination and creates its level forwarding information base or LFIB. If you place all these LFIBs side by side, you can visualize a logical end-to-end path. For this reason, MPLS is called switching. This is a very important paragraph and very interesting one also. So now what happens? Each router will be connecting, will be mapping or connecting, or rather creating a relationship between its local level and the most appropriate outgoing level. So see, R1, if we consider the previous picture, for R1, this level 1 was the local level, whereas level 2, 3, 4 and 5, they were all outgoing levels. But see, in this diagram, the local level is actually related with level 2. Why? Because this is the most appropriate level. Why most appropriate level? Because this level has been sent by my next hop. Obviously, level 3, level 4, level 5, they are coming from routers who are far away. They are not my next hops. So there is no point in relating their levels with my local level. I should be relating my local level with the most appropriate level, that is the level which is sent by my next hop router. Right? Now, definitely this concept, who is my next hop, has been given to MPLS by the normal routing protocols or any kind of routing process. So MPLS already knows that who is the next hop. So as R1 knows that R2 is my next hop, so R1 always considers level 2 as the most appropriate level. Now if you consider R3, you see R3 has this particular level information base where level 3 is the local and level 1, 2, 4 and 5, these are all outgoings. Now R3 will be relating its local level with level 4. Why level 4? Because definitely level 1 and level 2, they are coming from routers who are farther away. They are not nearer to the next hop. Although level 5 is coming from R5, which is definitely nearer to the destination, but still it is not my next hop. Right? My next hop, if you consider R3, my next hop is R4. So the level that is sent by R4 is actually my most appropriate outgoing level. Right? So in this way, they create a relationship between their local level and the most appropriate outgoing level. And this particular relationship is called level forwarding information base. Right? So this is level information base, which is a collection of all the levels, local plus the outgoing levels, and level forwarding information base, which is actually the relationship between the local level and the most appropriate outgoing level. Right? And if you place all these LFIBs side by side, you can visualize a logical end-to-end path. See, if you just draw a string between them, if you draw an imaginary string between them, so level 1 to level 2, level 2 to level 3, level 3 to level 4 to level 5, and finally to the destination. Right? So you can very easily visualize a logical or virtual path. This is not a physical path. Right? It is not a physical path like this. It is actually a virtual path. and this virtual path is ready even if that particular data has been forwarded. This virtual path has been created, right? So for this reason, MPLS is called switching, right? This is a very, very important fact. See, little while ago, I was discussing why it is called switching, why it is multi-protocol level switching, why it is not multi-protocol level routing. Now, as already experienced into networking, as all of you know, routing and switching, you must now understand the basic difference between routing and switching. See, we have come across several differences. Say routing happens at layer 3 or network layer, switching happens at layer 2 or data link layer. Then routing uses certain routing protocols, switching uses certain switching protocols. Switching can happen only inside a LAN, whereas routing can happen inside WAN, and all these differences. But the actual finest point of difference between routing and switching is how the data is actually forwarded, how the path is determined. In case of a routing motion, it is always a hop by hop motion. That is, there is no concept of any virtual continuous path, right? To make it even more simpler, there is no concept of any end-to-end virtual path if you are considering the routing process, right? If it is a normal IP routing, consider no MPLS is working here. It is a normal IP routing domain. Here, the path will be like this: a jump from R1 to R2. R1 knows only up to R2. Then a jump from R2 to R3. Then a jump from R3 to R4. Then a jump from R4 to R5. Right? All the routers, they only know that the data has to be tossed up and the data has to be received, just like tossing up a catch and receiving a catch, right? And the data goes like a bump motion, right? So it's just a toss up and toss down, toss up and catch down motion. Nothing more special about it. But if it is a switching process, then the devices who are participating in the forwarding, they also know that there is a path, there is a virtual path through which the data should be passing, right? It should not be just tossing up and catching down. It should be going through a particular path, right? Yes, it may look like that it gets tossed up and pulled down, but in reality, it is going through a virtual path, right? And that virtual path is actually decided by connecting these LFIBs. So once again, if you connect these LFIBs, you will find that they all indicate a virtual invisible type of path. For that reason, it is called a switching process, right? Now in this final step, we'll discuss what happens when the data finally arrives here. So when data enters MPLS domain, the first router or the ingress router adds label to the data. It is called label push. As the data moves in the MPLS domain, each router swaps the incoming label with the most appropriate outgoing label. The outgoing label is actually the local label for the next hop router. The next hop router very easily swaps this incoming label with the most appropriate outgoing label and so on. So each router is actually telling the next hop about its forwarding mechanism for that data. This is the most important advantage of MPLS over traditional routing. Finally, the last router or the egress router removes the label, that is label pop, and forwards the data in the no MPLS domain. Right. Before explaining this paragraph, I would like to mention that the level switched path, which is actually which can be visualized as a virtual path by connecting the LFIBs of the different level switch routers, is already present before any single data has passed. Very important point. This pathway, this virtual pathway, has been already established, it has been already signaled before any single data has come. Right. Now see when the data comes, what happens. So the path is already there. Now when R1 receives a data from a non-MPLS domain, R1 will attach level 2. What is level 2? Level 2 is its most appropriate outgoing level. So it will attach level 2 with the data. As this is the first time the data gets a gift, isn't it? It gets an ornament from R1. So for that reason, this is called level push. It is actually done by the Egress Router. So the data comes here with the ornament, or rather the label, that is level 2. Now what is level 2? Level 2 is actually the local level for R2. Immediately R2 understands that this particular level, my local level or level 2, is related to level 3, that is my most appropriate outgoing level. So I should be removing this level and I should be attaching level 3 to the data. This level exchange is actually called level swap, right? And this particular process goes on repeating until the data comes at R5. That means when R3 receives the data, it gets the data with level 3. What is level 3? Level 3 is actually its local level. It quickly understands that I have to swap this with level 4, right? Because that is my most appropriate outgoing level. Now what does level 4 indicate? Level 4 indicates that I have to push the data from F0 by 1, right? I don't have to just search which is the exit interface, what is the exit interface. I don't have to search. I simply know whenever I provide level 4 to the data, I simply know that I have to push the data through F0 by 1. That means if you analyze this entire incident once again, R2 sends a data with level 3. R3 receives the data with level 3. R3 immediately understands that the data needs to be swapped with level 4, and whenever level 4 is applied, I should be pushing the data through F0 by 1. Now I think it is clear to you that indirectly R2 has provided an information regarding what should be the exit interface for R3. Can you imagine? Have you ever come across this kind of a sophisticated movement if you haven't come across MPLS? Once again I repeat, R2 is indirectly instructing R3 as to what should be your exit interface for this particular data. So this is the beauty of MPLS, where your previous hop router is actually giving you the indirect instruction, some indication as to how I should be forwarding the data, right? And finally, the last router, that is the egress router. When the data comes here, there is no need for any label. So this router now extracts the label or pops up the label from the data and pushes it inside the non-MPLS domain. I think it is now very clear. It is not at all a very difficult story. When the data enters, it gets a label from the ingress router. As the data moves, the labels get swapped. What is the basis of this swapping? That is, I should be receiving the data with my local label, and I should be swapping this with my most appropriate outgoing label. So this is actually the logic for the swap. And finally, when it goes to the egress router, the egress router will pop up the label and forward the normal IP data towards the non-MPLS domain, right? And in this entire process, we have understood that the previous hop router is actually helping out the next hop router as to how to forward the packet. Understood? Now PHP. The full form is penultimate hop popping. In fact, the label pop is done by the last but one router or penultimate router, and it is called penultimate hop popping. The penultimate router actually receives an implicit null label from the egress router. Although it sounds difficult, it's a very simple concept. Let us come back to this topology once again. So what happens is, first consider this situation when this egress router receives a packet, MPLS packet with a label. So it has to pop up that label, number 1 point. And number 2 point is, now after popping out that label, it has to consult its routing table, because now it needs to forward it to the non-MPLS domain. So that means router 5 will be taking up a lot of time. A portion of the time will be to assess whether the data has reached the endpoint of the MPLS domain, number 1 point. That will take time, and then the next portion of the time will be consumed to find out what is to be done with this data now by consulting the routing table. So it will take a lot of time, R5. Now to reduce its burden, the label popping task is actually done by the last but one router or the penultimate router. And this is called penultimate hop popping. This is definitely the penultimate hop. This is the ultimate hop. So this is the penultimate hop. So the penultimate router will take the responsibility to pop the label. That means after the data comes to R4, R4 will extract the label or pop the label, and what it sends to R5 is simply a normal IP packet. Now when R5 receives that normal IP packet, it takes less time definitely to forward it according to its IP routing table. Right. Now a very interesting situation can come here. Suppose the MPLS domain is continued further. There is a R6 also. Whereas the destination 5555 is already here at R5. There will be other destinations which are connected to R6. Right. So the MPLS domain, let us assume that MPLS domain is not up to here. It is still extended up to R6. There is R6 also here, and there are also other networks connected to it. But our destination network or 5555 is connected to R5. Right. So try to understand this very clear. With respect to 5555, R5 is the egress router. With respect to 5555, R5 is the egress router. Whereas with respect to the other destination, R5 is definitely not the egress router. Right? The destination is connected to R6, and if R6 also belongs to MPLS domain, So regarding those destinations, R5 is not the egress. Their egress is R6. So if there is a packet going towards R6 also, going towards the destinations, MPLS destinations connected to R6, in that case, what will R4 do? Will it once again pop up the label from that data? Definitely not. Because for any destination that is connected to R6, R4 is definitely not the penultimate hop. In that case, the penultimate hop popping, this responsibility is done by R5. Right? Now, how come R4 understand that I have to pop up the label only for 5.5.5.5 and not for other destinations? How come R4 understand that I have to pop up the label only for 5.5.5.5 destination and not for other destinations connected to R6 and so on? This is because when R5 sends the label for 5.5.5.5, its local label for 5555, it actually sends an implicit null label for R4, right? So for 5555, R4 has received an implicit null label from R5. In my topology, I have mentioned here label 5, but what will be written in label 5? In fact, label 5, it will be written implicit null. So whenever R4 receives a label where it is for a particular destination, where it is written implicit null, R4 will understand that with respect to this particular destination, I am the penultimate router and I need to extract or I need to pop up the label for that particular destination. So this is called penultimate hop popping. I hope this is very clear. We have already discussed this thing. And finally, this particular page, the method of label allocation and distribution is called independent control label assignment with unsolicited label distribution. Once again, sounds very difficult, very complicated, but very, very simple to understand. So why it is independent? It is independent control because the label assignment is done regardless of whether the router has already received a label for that destination. It is unsolicited distribution because the labels are distributed to neighbors regardless of whether they need the label at all. So why independent control? If you consider the label information base, you can easily understand it. See, router 1, it has received a label from router 2 for this destination, but still it creates its own label. That is creation of the local label irrespective of the fact that whether I have received any labels from my neighbors. So this is called independent control. And why unsolicited forwarding or unsolicited distribution? Because see, router 1 has already received a label from router 2 and router 2 hasn't requested for the label at all, but still router 1 has passed over its local label to router 2. So whenever a router decides its local label irrespective of the fact that whether it has got labels, other labels from its neighbors or not, this is called independent control. And unsolicited distribution of labels because my neighbor hasn't ever requested for any label. Still, without any request, without any solicitation, I am distributing my labels to everyone. So this is unsolicited distribution. And finally, the label storage is liberal retention mode as the destination to level mappings are stored in the LIB from all downstream neighbors. This we have already discussed. This style, that is, I should be retaining the labels that I have received from every MPLS router of the domain, is actually called liberal retention. Because if you consider R3, there is no point in retaining this level 1 and level 2, right? Because definitely these are not appropriate levels. Forget about most appropriate. They are not even appropriate levels if I am targeted for 5.5.5.5. These two are definitely appropriate, and level 4 is the most appropriate. But level 1 and level 2, they are not appropriate, but still R3 retains them. So this is called liberal mode retention, right? And finally, this thing, this I am just reading out because in the practical, this needs to be shown in the practical also. That is TTL propagation in MPLS. I'll not go into the description or understanding of this particular point, because once again I'll be visiting this area when we'll be doing the practical part, because without the practical it is difficult to understand. But just go through it. By default, the IPTTL field is copied in the MPLS TTL field. It can be disabled by the command no MPLS IPTTL propagation or no tag switching IP propagate TTL. In that case, the MPLS TTL field starts from 255. Just for the sake of reading, I have read it. No need to think about it, because I'll be visiting this particular area. Once again, I start my practical, right? So that's all for this particular session. I hope you have enjoyed this session, and I'm also hopeful that I have presented the session in a way so that it is easy to understand for all of you. And finally, I thank you for all your patience and cooperation for attending my class. Thank you so much.